Hello and welcome to this Design Practice 2 Module 36. We are going to talk about introduction to mechatronics with an idea of intelligent product design. So we will try to decipher a little bit about what are the components which go into mechatronics as a field, how is it different than normal products, okay, because they are intelligent products, and then you apply this mechatronics concept into developing some of the intelligent products. Okay, so let's look into what really is this mechatronics. So it's a synergistic integration of mechanical engineering, electronics, intelligent computer control all together. And what we aim to do in this particular course is to design and manufacturing of products and processes which seem to be influenced by all these different domains. And there are many such products which exist, particularly let's say a car, okay, an automotive sector or an airplane. These are all intelligent products. There are controller signals which are being gauged in a manner so that they are able to do their job well through sophisticated computer control, okay, and a lot of feedback and tailoring the user signal to be doing the job in a manner that it should, so that the product performs well. There are many areas. You can have automotive, aerospace, medical equipments, defense systems, consumer products, even manufacturing, all the CNC processes, they are all driven through mechatronics. And if I were to look at holistically what this area is about, it's like a synergism between control systems, particularly digital control systems, control electronics, electronic systems, electromechanical systems, mechanical CAD or computers, all integrated together into one domain. Okay, so that the idea is that if the user signal is to an extent X, can I be able to, with feedback, improve that signal so that the performance of the system doesn't get altered too much, and it's a fine balance which happens to the real delivery from the product to the real world. Okay, so it's a very intelligently designed system. So how is it done? How is mechatronics practiced, or how is intelligence put into all the products? So you have various components of the system. So you have a mechanism in place which is more like the mechanical part of the system or the component. You also have an actuator which drives this mechanism. So this is really the power input and this is really the power output, okay, of the system. And the way that the actuator drives the mechanism is based on a sensory aspect which comes from a sensing tool, a small sensing tool, which will see how much motion or how much mechanical output is being delivered, and if there is a path correction which is needed, path correction will be done in accordance, okay, and that happens through electronic device which will again be able to guide the actuator by giving definite power outputs, so that the mechanical system can execute a motion, or the mechanism can execute a motion, or maybe some mechanical delivery of power, okay, in whatever formulation, whatever form, in a certain specified manner, okay. So that manner based guidance is what the job of a mechatronic system is really about. So when we look at the details of it, so you have an actuator which is powered from an external source, okay, and it generates a physical signal, and this physical signal is able to drive a mechanism which will give out the power of the system, okay. So on one hand you have the mechanism which is giving out power, delivering power in some sort, mechanical power mostly, okay, and then on the other hand you have the actuator which is doing this job of delivering power inside, so that the mechanism can deliver power outside. For example, let's say when we talk about an engine and a wheel, okay, so the engine is giving a power to a gear train, and the gear train is able to drive by making rotation happen through with the wheel, and the rotation is getting translated into a linear motion, okay. So you basically driving the wheel of a car through this whole process of actuation and mechanism, okay. But the important part is that how well the mechanism behaves also describes of how well the car runs, okay. So in that event, if power is available only at a constant manner, you may not be able to have intelligent guidance possible unless and until you basically take the physical signal, okay, in form of a sensor, etc., to see what is going on in terms of the operation or the power delivery of the mechanism, and then feed back with an intelligent electronic device the amount of power that would be necessary from as a function of time of this actuator through an electronic signal, okay, so that it can actually be able to guide the mechanism to a intended set of operation in an intentional manner. So all this intent based control is what mechatronics is about. So the first part, so there are many parts of this mechatronics based control. So one of the important parts is the CAM, CAD and the CAE, computer aided engineering part of the mechatronic system. So these are systems which are essential to realize or drive some of the mechatronic based intelligent systems. Okay, so this is one of the first steps of intelligent systems, I would say. So how are these related? How is computer aided engineering and design and manufacturing related together? So this is being shown here in this network. So you have one manufacturing tool, the rapid prototyping tool, which is based on computer aided design. So you have a CAD package, and this CAD leads to some data. You have actually done this, learned this towards the beginning of this course, and it is basically fed into a rapid prototyping tool, okay, to make a part or realize a part. So from the design to the reality, you are able to have intelligent computer control, okay. And then we talk about a management system, a component management system, which basically looks at the system level, what are the components which are needed and how these components can be formulated. And so there is an interaction between the computer aided designing and the component management systems, okay. And there is an integration of computer aided involvement of both the computer aided engineering based involvement of both the components as well as the system level information. You're managing the computer aided engineering information through the computer aided designing. You're basically feeding information from the computer aided designing into the CAE, okay, and on the other hand also using CAE to do the computer aided manufacturing, okay. So the systems are providing capability for rapid prototyping. Similarly, the components are providing capability for rapid prototyping. Again, the data that is needed for actually synthesizing what we have to synthesize comes out of the computer aided designing, and everything is managed by this computer aided engineering tool. So this is how the integration of all the three work out to be. There are different softwares which would do this job. For example, computer aided designing software, for example AutoCAD or TwinCAD, would do the job of how a design can be manipulated, maneuvered, stored in form of data, coordinate data. Again, many sections can be seen, or how they can be put together as assembly. And then the functionality part of that comes from the CAE, which talks about how you can assemble them together, how you can put them together in space, once the components or basic component level informations have been created. So the various packages like ANSYS, Abacus, Nastran, Adams, Moldflow, etc., to determine that part. And then we talk about CAD has obviously 2D drafting as well as solid modeling, and I think we have done a lot of this towards the beginning of this course when we talked about CAD as such. And so in order to integrate them, in order to make this CAE happen, where there is a functionality, a part based functionality as in a linkage or a mechanism or an assembly being realized, you need this manufacturing part, which is through SolidCAM or SurfaceCAM or MasterCAM. These are some of the softwares which would do this job. So in other words, we are having a computer based assistance and intelligence assistance for realizing a geometry from numbers to physical world, okay, through all these different things. The other thing we need to learn is about microprocessors and microcontrollers, and what are the different what are the differences between both, because they both go into mechatronic systems and they are intelligent systems with electronic control. So microprocessors again comprise of various different things connected together on a board, okay. So for example, there is a CPU which does processing. There is no RAM or ROM or IO on the chip itself, but there are different units. So there is a random access memory, there is a read-only memory, there is a input-output device again, but they are all on different they are all different entities connected together, and you need an assembly board to connect all this together. If we talk about a microprocessor, examples could be Intel's x86 or Motorola's 680X0. These are two microprocessors, for example. So you have connects between the CPU, the RAM, ROM, IO ports, timers, serial COM ports, assembled maybe on a motherboard. So there are many chips on the same motherboard, okay, and these are connected together through information sharing mechanisms, the buses, okay, which are again a short form of the Latin omnibus, which is actually which means that they are systems to handle data. So you have input output data, okay, being handled, and they are all connected together to formulate a general purpose microprocessor system. On the other hand, if I look at the microcontroller, the basic difference is, so it's a smaller computer, okay, and it has everything on a single chip. So you have on-chip RAM, ROM, IO ports based on a single chip here. Let's say, for example, this is a microcontroller chip which has everything in it. So CPU, RAM, ROM, they are connected together through various systems of systems, but then, you know, this is one entity rather than a board assembled with many components together, okay, which is formulating a microcontroller. So you have again Motorola's 6811 or Intel's 8051, Zilog's Z8 or PIC 16X. These are all different microcontrollers. So essential difference between both is that in a microprocessor, the CPU is standalone, RAM, ROM, IO timers are separate. A designer can decide on the amount of ROM or RAM that is needed, or even how many IO ports are needed. They are expansive in nature, very versatile, general purpose. However, microcontrollers are the only advantage they have is they are smaller and more integrated. So everything is together on a single chip. Okay, CPU, RAM, ROM, IO, timer, there on a single chip. You have a fixed amount of on-chip ROM, okay, RAM or IO ports for applications in which cost, power, and space are critical. Microcontroller would serve as a better tool rather than a microprocessor, because here we have to assemble a board on board, okay, of something. So, and then the microcontroller is only with a single purpose, okay, so it's programmed in a manner that will deliver only certain job. So let's look at again something which is very important to understand, what talks about PC based measurements and controls. So typically there is a PC board, okay, and you know it will acquire signals and it will try to help to plot the signals. This is probably an analog of what a CRO would do, that it would actually measure, you know, signals which are there in different circuits. This is the cathode ray oscilloscope, for example, okay. So how the data is handled is by many means. For example, you can have universal serial bus, USB based ports, you can have serial parallel ports, you could have CAN bus, okay, you could have GPIB. So all these different, you know, input output ports are utilized to talk to the controller, okay, which is assembled in the PC board, and use the various aspects of the controller when we talk about designing a PC based microcontroller, okay, or a microprocessor. So the whole idea here is that whatever sensors and actuators are integrated to an intelligent mechanism or an intelligent mechanical system has to essentially use some of these ideas together in order to function in a unified manner. And let's look at sensors and actuators. I think I have vastly described this in the MEMS area earlier, but a sensor is a device that converts an environmental condition into an electrical signal. Condition could be related to motion or related to you know, surrounding atmosphere with a certain dangerous gas, okay, something which creates a change, okay, and then we are trying to transfuse that into a signal which is more machine readable. And an actuator, on the other hand, is a device that would convert a control signal, usually electrical in nature, into a mechanical action, that is motion. It could be a motor rotating, for example, which will create rotary action. Through a linkage or a mechanism, we could transfer this action further into something, maybe a linear motion or maybe a periodic motion. So taken together, the sensors, actuators, controllers and power supply form the basic element of any control system. In it, if you look at discretely what these actuators would do, these are, for example, some of the actuators. This is a motor where essentially what is happening is that the magnetic field is being varied between different places from 1, 2, 3 and 4. Okay, so there is a rotating magnetic field on the stator which makes the rotor move, which gives you rotary power out of the system. These are some of the systems, okay, I'm mentioning. Again, there can be a DC signal given to the central shaft, okay, and a stator which is more fixed in nature with north and south pole, which could cause again circular motion to happen. There could be a AC based signal given to a magnetic coil which is there in a fixed magnetic field, and you know, the AC signal would ensure that the current directions alter, because of which there are differential Lorentz forces on both these components based on whatever is the static field, okay, and it will allow motors to rotate. The contacts in such cases are given through these contact brushes which formulate the basis of feeding the coils which are there in the rotor. So these are some of the actuators which would be conventionally used to create motion. For example, if you looked at anti-lock braking system in a car, so the system basically has a mechanical component which is being pressurized through oil pressure, which is controlled through a set of pumps and valves, and pumps are again controlled through motors. Okay, the idea here is that the distribution of the braking force is being monitored, and accordingly differential braking is provided mechanically to the 4 different wheels, both front and back. And in this case, so there are various speed sensors, for example, which will monitor what is the differential speed on the wheels, okay, and accordingly decide what kind of braking forces through the electronic control. If we looked at what are the different parts associated with different systems which can control this differential braking mechanism, so you have hydraulic assisted braking, which is actually through hydraulic cylinder on brakes, which you can find here, right here. Okay, so there is a mechanical aspect which is about how much braking force would be needed. So the hydraulic cylinders will provide just about enough forces, and that would depend on the pumps and the motors, which would allow the oil, okay, to go inside and create piston pressure, which will cause the disc brakes to happen. There is of course a wheel speed sensor which is there, which is based on some mechanism again, for sensing where mechanical motion is transduced back into electrical signal, and there is this ABS control unit which will determine how much of pressure goes to whatever wheels, in terms of pumps getting 4 different routes or 4 different oil routes to send to the different cylinders, okay, which will create the pressurization action at the mechanical level or at the wheel level. So it's a combination of the hydraulic cylinders which will create some kind of mechanical output. The wheel speed sensor will monitor the output, feed back to the ABS control, which will again create the solenoid pulse on the hydraulic line, whether it is the left front wheel or the right front wheel, or similarly the rear wheels, and then determine how much amount of oil should go or get distributed into these 4 brakes, so that exactly the required amount of braking is given differentially in both the different wheels. So you have a mechanism, you have a sensor, you have an electronic device and actuator all in place when we talk about such hydraulic system. There are many other examples. For example, mechatronics can be used from macro to micro applications. The figures here on the right show big objects, cars, stealth bombers, high-speed trains, which are based on some of these mechatronic principles. Okay. Again, you can have micro tools or consumer electronic products or even MEMS, which you have extensively done earlier, which would actually be direct application of such mechatronic systems. Manufacturing has a lot of applications demanded through mechatronics. For example, all the CNC machining processes where I explained to you there is a stepper motor or a DC motor, and there is a control, intelligent control based on a machine controller, okay, or a machine CPU, is all based again on mechatronics, where there are sensors which would be used as speed governors, or which will be also used to see what is the depth and feed and motion of the various racks, okay, which are able to align, de-align the workpiece with respect to the working tools. So these are again very high-end applications of mechatronics. There are advantages. This may deliver the highest accuracies and precisions and be able to create complex shapes. Needless to mention all this because I have done it extensively while doing CNC and CNC programming. This again is a mechatronic system for the seat module. How much reclining has to happen in the seat, or how much feed forward or feed backward has to happen based on the passenger size in the car is a very important question. So you again comprise electronic management system which will actually automatically, as the passenger comes in, there are certain cars where the seat would automatically manage, or even at the press of a button it will manage, so that there is a requisite ergonomic position for a driver of a car which comes into place, or as a matter of fact any other vehicles. So you have a seat architecture harness showing various smart connectors, interconnections together, which will provide a solution for any seating system, which is also mechatronics driven. Again, what can be done in space? This right here is a Phoenix Mars lander. It's a board which can collect specimens, do microscopy, electrochemistry, various different analysis on the same board. So it's an extremely complicated, again, mechatronic system, mechatronic assisted system, which will take a sample, analyze the sample, send the data, do all this intelligently while moving itself through a very complex terrain. Okay, so the advantage is this robot has that it can travel to other planets, take measurements automatically, and send and signal those measurements back into the ground station for us to be able to look at different aspects of planets and others, interplanetary space. So this is the range and expanse of mechatronic systems. I think I would like to sort of introduce this and close this particular module. But in the next few modules, there will be a lab activity driven by again the teaching assistant for this particular course, Mr. Sanjay Kumar, who will talk a little more about various aspects, individual aspects like sensors and transducers and how they work, and he will show you in the field by being able to set up a data acquisition based environment for different thermal controls which could be performed on a chip level. So with this I would like to end this particular lecture. Thank you, see you and goodbye. Thanks.